Okay, so we're going to look at motion down an inclined plane today. If you want to just sit back and enjoy the wonders, go ahead. If you want to write notes, go ahead. If you want to print out notes and fool you later, go ahead. Do what you want. Give me crack corn, I don't care. I'm going to talk about motion down an inclined plane. You will today calculate the forces acting on an object resting on an inclined plane. This will include the normal force, friction force, components of the gravitational force, and we will calculate the components of F gravity exerted on an object resting on an inclined plane. In other words, I'll tell you everything you need to know about inclined planes. It's your fancy words for ramps, right? It's actually warming up enough in here that I think I can. Yeah, no. I hear all this stuff. Would you say? Thanks.
It's going to be on the recording too.
You can listen back and enjoy it. What would you say, is there any angle, you don't need to write this down, just watch. Is there any angle that is equal to that one that I just wrote as theta? Is there another one somewhere that would change the same way? Now normally I would do this. I would go over here, but it won't show me. Oh, that's so maddening.
Try and read.
I did.
Control delete.
Try turning it off, turning it back.
No, I didn't do that. Good point. Is there any angle that would get bigger as this one gets bigger?
Yeah.
Yeah? Where would it be, Ty?
No. It gets smaller.
Where? Like up here?
No.
In this triangle?
Yeah.
Which one?
I don't know what
Here?
to ask here.
I'm still confused.
What angle are you at?
Well, would that angle there, like let's say this angle, let's say the blue angle was 35 degrees. Would the red angle also be 35 degrees?
Yeah.
No?
What is that angle for? What is it like?
Well, it's just this, like this would be, and I'm giving you some previews kind of here. This is the trailer, if you will, for today's lesson. If that's 90 degrees right there, right? Like the normal force, would that angle change in the same rate as this one?
Yeah.
Yes.
Like as you get steeper, think about it, sorry there.
You get
Sarah, I'm gonna look at the table again here, right now.
Yep. Why is there an angle there? Like.
Well, right now, what's the red angle?
Like
0.
Is it not 0, the red angle?
Yeah,
Because it's just flat, right? What's the table angle?
0.
Yeah.
Oh.
Now the table angle is like 10. So what's the straight down to, like, straight down, which is through the middle of the book, and then perpendicular. Would that be 10 degrees as well?
Yeah.
Yeah.
Oh.
Yes, it would, right? Right? That angle there changes as the blue one changes. Okay, so I'm going to kind of talk about all this stuff. I've given you the preview. Here's the good stuff. When an object sits on a flat surface, gravity acts straight downward Fw. True?
True.
True. The surface exerts a normal force, Fn, correct? And when it's on a flat surface, in this case here, this is Fn and this is Fw, would you say that Fw equals Fn?
Yes.
You should say that's true. What happens when the surface is at an angle? Will those be equal to each other?
No.
No. Yeah. No.
No.
I'll say it again. Think your answer through before yelling it out. When the surface becomes at an angle, like if this whole thing gets rotated, will the weight force be equal to the normal force?
I don't think so.
Is the weight force not always straight down?
It's towards.
Straight down towards the center, right? Right? So when I do this, it's no longer pointing straight down. So now, should it be? Should be.
That's for angle.
Right? Should be. Okay, so let's go. Oh, let's get over there. So when an object sits on an inclined surface, let me just do this here.
Oh, so it wouldn't be like this anymore.
When an object sits on an inclined surface, gravity acts straight downward Fw, and the ramp exerts a normal force Fn. But they are now like this. and I'll give you a chance to jot this down in a
Yeah,
second.
see, that's what I-
See, this is FW,
And then if you
and FN would be
Yeah.
like that, right? Okay, I'm going to pause there. I want you to write that down. Now my next question to you is, or my next statement, is there now, before, don't freak out,
Okay.
what's the net force right now?
Here.
0, which means if the object's at rest, like the book is, then it's going to
Stay rest.
stay at rest. But now when I increase the angle, now I actually have a net force, don't we? How do we find the net force?
Finding the angle.
You got it. Well, you got to sort of
Oh.
add vectors, right? Which means the sum of these two. I've never done this before. I just realized that the net force is now actually down the ramp.
You drew those.
I did, didn't I? Man, am I good at what I do. So now, because the net force is down, it's going to actually accelerate down the ramp. Is it not? Makes sense. Bingo.
You should be teaching.
Now, having said that, as soon as that black net force is there, because the object is now moving, what have we got? Because it's moving, we now have another force that gets introduced, which is
Drag.
or friction. Right. Well, I mean, you're right. You just called it something different, right? You have a small amount of friction. Say again? Oh, it could be much bigger, right? And then as it gets bigger, what's going to happen to the black one?
Yeah, we get smaller.
Really?
I don't know.
Crack me up, Brad. Is it not going to get bigger?
Yeah.
Like as I went higher and higher, is it not going to like more? Absolutely, right? Because this angle is going to change, right?
Never mind.
And I wish I could draw it, but
I thought you were talking about it.
okay. So what we're going to do is we're going to label these. Okay. So let me just make sure I get this straight because I don't want to screw this up because I've done a really good job of getting you to here, so I don't want to screw this up. Okay. So what I'm going to do is this. I'm going to erase that black one for now. I'm going to draw two more right in here. Okay? So FW is straight down. Now, what I've done is, you know how we've had like up to now, we've had like here's F1, and I've said like this is F1Y, and this is F1X, right? X and Y components. We've kind of talked about that, right? Like FAX and FAY. Okay, X and Y components. Well, now imagine that the X is up and down the ramp, and the Y is this way. So we've taken that whole XY and kind of twisted it a bit.
Do we write this?
No, just watch. Just watch, okay? I've twisted it. So now, I'll get rid of these guys here. Hey, didn't want to do that.
Lost now.
Okay, so I need a label for this. Well, to make things a little bit simpler, I'm going to label this FW. I'm going to label this one FN. And I'm going to label this one FD. Now, these are my own design. You will see this different in a textbook, I think, in a more complicated fashion. But what I just showed you there with that rotating X and Y frame might help you when you get to that point. So FN and FD are simply the components of the weight force. Here's the weight force, kind of like the overall one. And FD is simply the part of the weight force that is acting D down the plane. It's kind of like FX for FA, or FAX for FA. It's a part of the FW. Okay? Maybe if you want, we could write in here FWX, and I'll use air quotations for the X because the X now means
Yeah.
up and down the ramp. I know Mr. Smigalski likes to teach that way, the X being up and down the ramp. And then this would, what would this one be? FN would be equivalent to what? FWY. That seems to be me to be a little bit overcomplicated, so I'm going to call them FD for down the plane, and FN for it's the normal force. It's technically, it's not FN because FN is actually the up. It's the equivalent to Fn. Some books call it F perpendicular. It's the component of the Fw that is perpendicular to the round.
Upside down T.
I've given you a lot of different versions of it. I get that I might have confused you. I'm going to simplify things here. Okay, once you see the formulas, it'll be fine. Some people will go, okay, yeah, I get it. Some people say, I don't get it. You probably don't need to get that, but some of you should need. But what I'm saying is that these are simply components of the weight that pull it down the round. Fd pulls it down the plane, Fd, and Fn affects the friction because, sorry, Karen. This is fun.
Yeah.
Who, me or her?
You. I can't see you guys.
If I increase the ramp angle, I'm actually increasing or decreasing the normal force. I'm decreasing the normal force, right? Because I'm increasing that angle between. So at some point, because the normal force is less, the friction force can now overcome it. Come on. Oh.
I knew it that time.
Yeah, I went too high. Okay, now I'm going to sum it up for you. That was more sort of the, oh yeah, okay, I kind of get it, I kind of get what's going on. Do you need to write any of this down?
No.
Probably.
You should probably have this picture.
Oh,
I am going to do a sample.
Yeah.
Going to do a sample, don't worry. Right? But I needed to introduce you to this concept of Fn and Fd, and again, those are my own sort of names for these.
Why don't they just use one that's like...
People can't agree on anything right now. We can't even agree whether you should wear your hat inside or not.
What?
People are...
Yay!
I told them.
Okay, here's where I'm going to derive the formulas for you. Okay, this you should probably write down. This you should write down just for, I haven't gone through an example yet, I'm doing theory. Just doing theory. So from that triangle, right, and this triangle is a right triangle.
No, it doesn't matter because
Fw is straight down, weight force, which is mg, right? Fn and Fd. Now, because it's a right triangle, we can apply good old Pythagoras, so trigonometry, I guess. Right? Is the Fd opposite or is the Fd adjacent?
it's opposite.
It is opposite, so we're going to use sine or cos?
Sine.
Sine. So if I had to write Fd equals, you would say?
Sine.
Just sine? Just it? Just sine?
I don't know.
Your FD.
F sine theta is Fd over mg. Opposite. Oh, let me show you. Sine is opposite Fd over hypotenuse, which is Fw. Fd is equal to mg sine theta. Right? If you rearrange this for Fd is equal to sine theta times this, m times g. Fw
That doesn't make sense.
Mass times gravity equals...
is equals Fw, absolutely. That is a formula.
I wasn't listening.
So, box it up, wrap it up, put it under the Christmas tree.
Putting it back.
That's the present. Fd, the component of the gravity acting down the plane is equal to mass times gravity times the sine of theta. And as the angle increases, the sine of the angle increases, which means you get a number that's closer and closer to 9.8. What's the sine of 90 degrees? Anyone know? Punch it in. Sine of 90 is? It is 1. Because it is.
Because it's just a right angle.
It just is.
Unit circle. Sine of 90 is 1, right? So if it's 90 degrees, in other words, the current table is at 90 degrees. No, I'm not going to put it 90, but if it was like right up like this, right? M times G. I think I'll know what you do.
Hey,
So much fun getting terrified. Okay, so what's going to be Fn? What's this one going to be?
Cos.
More, Johnny.
It's just gonna be cos. Yeah.
Cos theta is equal to Fn over mg. Adjacent over opposite, right? Adjacent over adjacent over hypotenuse. Adjacent over hypotenuse. And that's so in other words, Fn is equal to mg cos theta. Those are the two formulas. That's all that theory. I basically did a formula derivation for you.
This one was a lot easier than the other ones.
Well, yeah, not as much algebra, but more sort of thinking, right?
I don't like these ones.
Really?
Those are the formulas you're going to use.
Wait.
Now, you might be lost. That's okay. Right? All you really need is now these new tools that I've provided for you. Right? Some of you will get the reasoning behind those. That's okay. Some of you won't. Okay, I'm not testing you on the reasoning. Right? Okay, let's do a sample question. You don't have a sample question, do you? Okay, I'll pause here. Write that down. Draw the picture. Those are the things we're going to find. I'll give you 3 minutes to draw it down.
Yep.
All right, so I'm going to draw on here that little diagram again, right? Because you should be, basically what I'm saying is, Danielle, basically what I'm saying is you should draw a free body diagram to begin with, right? And I always recommend start with the weight force. Weight force is down. This one here is the normal force, or if you prefer, the component of the weight force that is perpendicular to the plane, which is way too hard to write out.
Yeah.
And then this one here is the FD. Now, this FD, if you want, can be just shown on there as well. But I'm going to draw it down here so that you see the triangle. But at some point, I'll start doing just this.
Okay.
Yeah. Oh, yeah. I mean, the weight force is easy to find, right?
Yep.
Okay, so I got to remember 30 degrees, 5 kilograms. That's all I need. Okay, so find the weight force. Fw is equal to mg. What did I say it was? 5. So 5 times 9.8. Now, here's the classic. Should it be minus 9.8, Mr. Bennett? Well, okay. No, I can't. No, sorry, I can't. No, bear with me. The negative in minus 9.8 simply means down. But that was before. That was when all we had was things going
Up and down.
up and down. Now we got things going on an angle. Okay, so now remember I said we had this kind of thing, right? Where this is the x and this is the y. And I said, is it okay if we take that whole thing and
Shift it.
right? So could we define, for the scope of this question, could we define as down the ramp negative and up the ramp positive?
Yes.
We could define that, right? And that's good because they have to be, positive and negative directions have to be opposite to each other, right? So down the ramp is certainly opposite to up the ramp. And as long as I say that, it doesn't matter whether it's 30 or 38 degrees or who cares, right? Down is negative, up is positive. We can do that.
Yep.
So, so does the minus, go ahead.
Will we get marks off on a test if we put positive?
If you want to define down as positive, go ahead.
Okay.
As long as you define it like
Do
that,
we have to
right?
clarify?
So,
It'd probably be a good idea. Convention is down is negative. Okay, hang on, Ty. So what I'm saying is, do I need to put the minus 9.8 in here?
yeah.
Well, you can, except that negative is really like up and down, and we're not really, the thing ain't moving up and down, is it?
Because you're trying to find that.
Right? So you go right ahead and put negative in there if you want. This is going to be what, 49?
Yeah.
You want to put negative if you want, but be aware that that negative is actually like down, not down the ramp. Okay?
So you're talking about the weight force because it's just like
It's straight down.
Right.
They're both correct, Perry. Just you're going to have, things are not black and white anymore.
What?
So
Yeah.
it's negative.
Okay. Now, what is the normal force? Fn is equal to
FW.
mg cos theta, right? We got that just 2 slides ago. Fn is mg cos theta. So the mg we already know is going to be the minus 49, but let's write it all out, I guess. So it's going to be 5 times 9.8 times the cosine is at 30 degrees. You can do that, either one. Is it 30 degrees?
Yeah.
Okay. So 5 times 9.8 times cosine 30. 42.4. Okay, now, what direction is the 42.4? Well, it's really,
Going down.
it's not really anything. It's like, so let's just maybe just keep that in the back of our head. Let's not assign a direction to that. Maybe we don't need to assign a direction to it, right?
Why was it 42 point what?
It is in a certain direction, but we can sort of hang on to that for the time being. We've got a picture of it. We know where it's going.
Okay.
If we need it to be a positive or negative, then we'll make it eventually. Because the positive and negative just is a direction. That's all, right? That's all it is. Okay, so what about FD? Well, that's going to be mg sine theta. Johnny got it. Mr. Abbreviation. Or should I say Mr. Abbrev?
That's a good one.
Nah, it's not that good, actually. Kind of lame.
It's okay.
24.5. Now, the 24.5 is down the ramp, right, or down the plane, which I said is negative. A different sort of negative, right?
Going down.
Let's just write down the ramp for now. Is that okay? Can we just write down the ramp as the direction instead of negative? Why not? We can do that.
So much more sense.
Half a negative sign. How do I know it's not just a small one? You could make up a direction for that, but what would happen if it's not 30 degrees? What if it's 40 degrees? Is that not a different direction then? It's just like, yeah, but it's, what if it's 90? Then it's straight down.
Then that's a full negative.
Let's just hold off on this direction thing for the time, until we know we need
You
it.
didn't write this.
Okay, now what is the net force? Let's go back to my picture. Is there any friction here? There is no friction, right? And so, the FD is, remember when we added them before? Right? I had this one, really. The F net is really the FD. The F net is the FD. How come? Because there's
no friction.
no friction.
So that in this case, FG is.
In this case only, the F net is the FD because there's no friction. Because this guy here and this guy here are going to be balanced, right?
So the FG is
The FD is the part, the component of the gravitational force that acts down the plane. It is the applied. Well, it's, but what's it applied by? By gravity, right? It's not really applied by anything. It's just the part of gravity that's acting down there. Yeah, it's gravity. Right.
So, would you still have to, like, if there was friction, would you still use FD? And
Do you want to skip ahead to talk about gravity for a second?
Yes.
Or, I mean, friction for a second?
Yeah, I want to know what you just.
Okay, well, it's come up. So if the FD is this guy here down the plane, which direction is going to be the friction force?
the other way.
This way, right? And I did the trailer on this already, right? So that's why I need that negative down and the positive up, because I'm going to have to subtract friction.
How is confused by saying that?
Yeah, because you put, it says like A net and you put F net.
Well, because, yeah, no, they're not the same thing. That's a good question, Harry. I need F net. F net is equal to MA, right? F net is equal to MA, but my F net is my FD, so that's going to be my 24.5. 24.5 is equal to, is it 5 kilograms? 5a, right? So it's 24.5 divided by 5, 4.9. And as Ty stated way back at the start, the acceleration is going to have to be less than 9.8. If you get an acceleration of greater than 9.8, you got a problem. Because there's no way it can be more than 9.8 if it's going down a ramp.
You're lying.
Down it can't be, but what if it's going up?
I guess it could be if you applied enough force, right? Can objects move up ramps?
Yes.
Are we going to deal with objects moving up ramps?
No, no,
No.
no, we're not.
Oh, yes, we are.
Oh, I'm not.
How does not make them up?
What is that? An A? Like 4.9?
A, the net acceleration is equal to 4.9.
Oh, 9.
And I guess we really should say, in what direction?
Down the ramp.
That's science.
Down the ramp. If you want to call it minus, you go ahead. Down the ramp. Okay, now in part E, time to get to the bottom. Now we're talking about a kinematics question here. To get the time, I got the A, so I have the VI. What's the initial velocity of this thing?
0.
0. So I got the VI, I got the A. Do I have the distance?
Yep.
It's 1. I need to find the time to get to the bottom. I'm going to use D equals VIT plus 1/2 AT squared.
You lost.
Really?
No.
That's the simplest one.
I like it. I don't like the one where they're both squared.
Wow, there's something squared
I
again.
know, it just scares me.
1 meter, right?
Yeah, because the ant's so big.
Mhm.
VI is 0, so VIT is 0. Plus 1/2 our acceleration of 4.9 t squared. Now here, if you put that 4.9 as negative, you're going to end up
With a weird answer.
with a weird, so just be careful, okay? Don't get hung up on the positive and negatives. Just keep in mind they mean directions. Okay, so I'm going to have here 1 is equal to 1/2 4.9 t squared. So t is going to be the square root of, now can you do the manipulation in your head here?
What manipulation?
Well, I want t all by itself. So it's the square root of, because I'm going to take t squared, square root. This is the 4.9 divided by 2. The 1/2's going over to the other side, so it's going to be a times by 2, right? So it's really 1 times 2 divided by, no?
Okay, I understand.
Okay. Okay, well then do it this way if you want. Okay, so 1/2 4.9 is 2.45. So t is going to be the square root of, no, 1, I got to get rid of 2.45 times t, so it's 1 divided by, right? It's 2.45 times t squared.
What is going on? You lost me now. I'm done thinking. Maybe.
I mean, 2.45.
It's not the square root of 2.45.
Okay, but 1 divided by 2.45
Is 1 divided by 2 is 2?
No, go 1 divided by 2.45, get that answer.
Oh. Well, I like to think we're a little bit beyond that, but maybe not. No, I'm just saying, you guys should be able to handle that. I'm not calling anyone dumb. Just saying that at some point, you're going to have to deal with this. It's all going to be the same thing.
Oh, I'm scared.
I get 0.64. By the way, if you took the square root of 2 over 4.9, you get the same thing. You're going to have to be able to do that mental manipulation.
You
at
had
some
me
point.
until like the very last thing.
What's behind the 4? 0.64 seconds.
Oh, that's second.
Second.
That's not a.
Oh,
Time. 0.64 seconds.
Yeah, I know, we both did.
I made it one step.
A 2.45x square root of 6 square root of
Right. How do I find the velocity at the bottom? Oh.
That's square root of I squared.
Yeah, right? We could use Vf squared equals Vi squared plus 2AD, right? Vi is 0, acceleration 4.9, displacement 1, so it's going to be okay. What's the single step of this? Probably. Vi plus HE, absolutely. This is going to be the square root of 9.8, right?
This
3.13.
This is still not killer.
Wow, that was hard.
None of this is really, the only new part is this, and we only use this to get FD, which became our FNet. And once we get into friction, then this one will come into play a little bit more. Okay? We are currently talking about frictionless ramps.
Wait, can you go back to go down?
Yeah. Because you've got to understand it before you can understand the mumbo jumbo. To make it simple, you gotta understand what's going on behind the scenes. Okay, so pay close attention. On a frictionless surface, is it true that FNet is equal to FD?
Yes.
So this means that FNet, no, just watch for now, then you're right now. FNet is equal to MA, right?
Yeah.
FNet is equal to MA, but FD is equal to FD is equal to mg sine theta.
Oh my goodness.
What's going to happen here?
So we got one more note.
That makes
Bruh.
Let me state this very clear, on a frictionless surface,
So that's only.
on a frictionless surface, when the net force is the FD, Fnet is equal to MA, FD is equal to mg sine theta. You can cancel the masses because the mass don't matter. And the acceleration is equal to g sine theta. Again, only on a frictionless surface.
Where do you get A from?
Well, look at it. It's still right
Oh,
there.
never
Fnet is equal to MA, right? I canceled the M on this side. I'm left with A. I canceled the M on this side. I'm left with g sine theta. The acceleration on a frictionless surface is g sine theta.
That makes sense.
So then what would you do with the FD?
With what?
Like,
You don't have to do anything with the FD. The FD, I've simplified it.
okay.
The FD has disappeared. Really, if you look back here, look at FD is equal to mg sine theta. I've got to multiply by 5 in there, right?
Yeah.
Look at, see, I've got 9.8 times sine 30 times 5. Guess what? A little bit later, what do I do right here? What do I do in this step right here?
You already find out.
I'm dividing by 5. Here I'm multiplying by 5. When you multiply by 5 and divide by 5, what happens?
It cancels.
Cancels out. Okay. The textbook has several ramp questions. They are on page 152.
How do you know they're frictionless surfaces?
I believe they're all frictionless. I could be wrong. Tomorrow I will deal with friction on ramps. There's some in the handout. The ones in the handout are kind of made by me. They're kind of very basic, generic. There's no fancy, like it's just, here's an object, it's on a ramp, have fun. Right?
You would use the F parallel too.
Oh.
Oh, no.
Okay, perpendicular you mean?
Yeah.
Yes. So F perpendicular is equivalent to Fn. Yeah, I really got to use a more consistent approach. I know.
Who is shaking your
Yeah. The textbook has fun questions like cows on roller skates and stuff like that.
Yeah, but
I think it's a lot.
Okay, my turn to be quiet.
conversation.